Tze Ping he was born in Penang, Malaysia. He obtained his undergraduate medical degree from the Royal College of Surgeons in Ireland, Penang Medical College, and undertook his fellowship at the Royal College of Pathologists in the UK, training in chemical pathology at the National University Hospital and Singapore General Hospital. He currently serves as Consultant Research Director at the Department of Laboratory Medicine, National University Hospital in Singapore. His areas of interest include mass spectrometry testing, and he is part of the Asia Pacific Federation of Clinical Biochemistry, mass spectrometry working group also, and is invaluable there, which is not written on his bio. I'd like to invite Tze Ping up to give his presentation.
Hi, thank you, Rhonda, for the kind introduction and for hesitating for just a little while trying to say that I have a nice personality. It does give a lot of credibility to that statement. So I'd like to thank the organizers for the invitation and thank you all again for attending. I have no conflict of interest to declare. And to be honest, the real reason why I'm standing here speaking to you all is not because I'm a mass spec expert. In fact, my laboratory used to have a mass spec, but after we validated it, we've done the dual reporting, we couldn't get it actually implemented clinically because we have someone very powerful who is a clinician who actually blocked us because they wanted 24/7 service, which we could not support. So the reason why I'm here is because I missed 2 out of 3 of Rhonda's most recent teleconferences. So as a punishment, she's making me standing here talking to all of you. Another hidden talent of mine is actually the ability to talk about QC long after my wife has fallen asleep. So I hope I don't bore you in that aspect. So let's examine mass spec as an analytical instrument. It is a very powerful tool, but it has a lot of manual processes, as we've seen in past lectures. It comes in 2 distinct parts, usually a separation part as well as a detection unit. So the separation unit is usually a chromatography, and the detection unit is usually a mass spectrometry, or a mass spectrometer. Oftentimes, a lot of the protocols are developed in-house. A lot of the reagents are prepared in-house as well. And often we have assays with very wide dynamic range, which is actually a strong advantage of mass spec in the first place. And the testing are often done in batches. Analytically, it may be more sensitive than immunoassay, and that is, on the one hand, is a strong advantage, but on the other hand, it is also something that we should be mindful of when we design our QC practices. And a lot of times also is the mass spec, as we saw in the preceding lectures, can be multiplexed. It's very powerful. It has a lot of detection power so that we can actually multiplex the assay. And we've seen an assay with 14 analytes that it can measure in one go. So all these actually has some implication in the way we should consider QC practice. So some questions that I'd like to ask. First of all is, do you run any internal quality control for your mass spec tests? Yes? Most people are nodding yes. The reason why I ask this is, as I've shared on Monday, someone from my hospital, a liver surgeon, is developing a mass spec assay for clinical translation. And he told me, so I asked him, hey, because him being a liver surgeon, I asked him, so what's your QC practice going to be like? He's like, nah, you know what? This multi-million baby doesn't need no QC. So I was thinking of telling him, well, good luck buying a Lamborghini and not servicing it. So good, we all run QC, but do you think QC, internal quality control procedures, detects error prospectively or retrospectively? Does it detect errors that happens in the past or into the future? Do we think it's in the past? Yes? Most people think it's in the past. Anyone thinks it can detect errors into the future? Yes, as well? Yeah? Okay. So, where do you usually place your QC concentration at? That means, in the full dynamic range, where do you usually place your QC concentration? How many QC levels do we usually run? 1, 2, 3, 2? mostly 2, 3. So Rhonda recently did a survey as part of the APFCB 17 OHP harmonization project, and we surveyed 43 laboratories, more or less, around 40 laboratories. And it is very surprising, or it comes as a surprise to me because I'm very interested in QC, that for clinical mass spec laboratories who are running patient samples, the level of QC can range from 1, good thing it's not 0, 1, all the way up to 6. So there is actually a very wide discrepancy, practice in this regard. So do we use the same QC procedure for multiplex assay as we do for monoplex assay? Yes? Okay. So, sorry. I have only 6 QC issues to discuss with you. And I try to make it, sort of a bit more cute because it's already end of the day, right? So we don't want to keep it more too serious. So first is think about the end. Second is know yourself. Third is level the playing field. So fourth is hit it where it counts, risky business, and stay the same. So what do I mean by that? So think about the end, meaning that QC is actually retrospective. When we run QC, it only tells us, or as far as I understand, when we run QC, we are only assessing the analytical performance up to the point where we run the QC, that it's still valid up to this point, given a statistical uncertainty. What we don't know is that immediately after the QC, the instrument can immediately break down, right? So QC, in that sense, doesn't help us predict future error. But given enough data, we know that this is the performance, the usual performance of the instrument, and therefore, if the QC is within range, the likelihood of an abrupt error is less likely. So, in that sense, it's always useful when you run a batch of samples to have QC sandwiching, to have QC at both ends to sandwich the patient samples in between, so that we know before we start, the instrument performance are okay, and at the end of the test, in between, it's likely that the test performance is okay as well, okay? Another thing to think about is that if you run a batch of 20 versus a batch of 2,000, then obviously we should also include more QC checks in between. The reason is because we want to be able to pick up errors whereby we can more easily correct them when we encounter a clinically significant analytical error, okay? And I give you a real example. This really happened in my lab. Okay, we had one day, as I was telling someone, Friday, 4 or 5 p.m., I had a 7 p.m. flight back to Penang. My head of department called me and said, hey, you know what? Our lab had a big issue. One of the instruments had been reporting falsely elevated 2 to 10 times higher values than what it should be on our Immunolite assay on the Siemens platform. And when we looked at it, the QC at the start of the day was okay. But immediately after the QC run, everything subsequent to that, 63 tests, tumor markers and hormone markers, all were 2 to 10 times higher. So this is just an example of how QC is helpful to the point where we actually run it. It tells us that previously it's likely to be okay. But prospectively, we don't. So in this case, the trouble that I had, or the reason why we didn't detect this error, was that although we run these Immunolite assays in batches, we run QC at the beginning of the batch, but not at the end of it. Yeah? So we missed the error in that sense. So know yourself, which is to know the performance of the mass spec assay. So in the core lab or the routine laboratory, we are very customized to determining sigma values or determining the performance of our assays. But it's probably useful to do the same for mass spec assays as well. Because in the best case scenario, mass spec can outperform immunoassays, but sometimes, given some technical challenges, the performance can be quite similar to immunoassay or sometimes worse than it. So it's often useful to know where the assays stand in relation to the analytical quality specification. So, moreover, we should also do multiple assessment for multiplexed assay. We should not treat the different analytes as though they are the same. The reason is because you can have some tests that are high in abundance, and we can measure them very well in the multiplexed assay, but some would be very low abundance, and therefore we will have difficulty measuring them as well. Okay, so once we know the sigma value or the performance of the assay, then we should actually dedicate we should dedicate more QC for poorer performing analytes. Yeah? So if a test, we know it's performing less well, we give them more attention. It's like if we know we are poorer in one subject, we go for more tuition. So different analytes in a different, in a multiplexed assay may also require a different QC consideration. Okay? Prioritize the poorest analyte with the highest risk and customize QC rules for others to minimize false rejections. Okay, so this is one way we can do that. This is a power function graph that most of us are familiar with. This is from the Westgard website. So you have 6, 5, 4, 3 sigma. Thank you. I actually have my water here. Thanks. Thank you very much, Rosita. So if you have different assays with different capabilities, then you should design the QC using different QC rules as well. Yeah. So hit it where it counts is choosing QC concentration carefully. Consider how the analyte is being used, especially for very low concentrations that are clinically important. So for example, for toxicology or for some hormone tests, the lower concentration is extremely important. And contrast that, for example, to vitamin C, then, well, Andy may disagree with me, but contrast that to vitamin D, perhaps not detecting as well at the lower concentration is less important. Yeah? So think about the clinical implication or the clinical use of the tests when we design the QC strategy as well. So a small shift can easily occur, particularly at the lower end, and may easily change clinical interpretation. So if you have an assay that is clinically very important at the lower concentration or the lower limit of detection or quantification, it is important for us to actually anchor a QC there, okay? Because we have a lot of examples in immunoassay whereby this is actually not done. For example, for troponin PSA that we've seen in immunoassays where we don't have a QC anchor it at the very low end, and there is actually a false positive shift, and therefore causing a lot of false positive results as a consequence, okay? And if you have to choose 2 QC, and if you have been given only 2 QC levels to run, the best bang for buck is always at the extreme ends of the assay, if you can actually design and achieve it. The reason is because if you think about it, oftentimes what we are monitoring is actually the calibration curve stability, right? So the calibration curve should be a straight line. And it is, when it fluctuates, it tends to either tilt down or tilt up, or it can shift up and shift down, right? So either way, the extreme end is the part that gives us the most information because it's the most sensitive to any shift. Yeah? So if you have only 2 levels, you try to bring them to the extreme ends, then it will be the most sensitive for detection of any error. So risky business, consider the clinical risk of getting an analyte wrong. So risk equals to probability times severity, and then it's actually compounded by multiplexed assay. Yeah? So we should actually consider dedicating more QC to more risky analytes or assay. And this is the one that I'm less certain about, which is considering performing between reagent lot comparison. In immunoassay, we often, each time when you change a reagent lot, we have to do reagent lot comparison, right? You know, you run 10, 20 patient samples, and then you do either a comparison of mean or a regression line. But I'm less certain whether we do this for mass spec assays in the routine laboratory. But if you think about it, if you buy a new batch of reagent, or even after a while, there's a possibility of the reagent deteriorating and drifting downwards, right? So maybe it's good for us to actually periodically run sort of what we call a between lot verification. That means you just run a few patient samples that we've kept in the past and we have a past value, comparing it to what we are doing currently. And just to see whether there's actually a shift or gradual drift in the assay performance. Because sometimes what we can overlook is that there is a small but accumulative drift in the assay that we may miss if we are not careful. Okay. So this is what I mean by cumulative drift, because when we do between lot comparison, oftentimes we set a tolerable limit, and if the calibration curve shifts a bit, we accept it. But the next time, when we re-examine it, this is the new baseline, right? So there's a new tolerance, and it can go up again, and go up again, and go up again. So we may end up accepting a very large cumulative shift without actually noticing it. So in summary, the 6 quality control consideration is, first of all, to consider running QC at the end of patient testing on top of the beginning of it. Know the analytical performance of each analyte, and then devote more QC to poorer performing analytes. Choose QC concentration carefully, particularly for very low concentrations testing. Consider clinical risk of the analytes and how we use it, and do comparison studies periodically, if not when we change or when we purchase a new lot of reagent. Yeah. And beyond internal quality control, there is a high requirement that we should pay attention to mass spec because it's so sensitive. Not only because it's analytical sensitive, but because it has a lot of moving parts as well. So we need to monitor instrument performance more closely and have a QC, sort of have a QC for instrument performance, not just for the assay itself. So what do I mean by that? There is a new, this is actually a recent publication, which is very nice, that proposed the use of a system suitability test. What this is essentially a test, sort of like an internal control, but the interpretation of that QC is for the performance of the analyzer, and I'll explain a bit more. So test is performance suitability of measurement system prior to patient testing and helps in troubleshooting and allows longitudinal assessment of performance for prevalence for preventive maintenance. So this is basically having an analyte and an internal control in an extraction or reconstituted solvent for the assay, okay? And include any closely eluting substances where relevant. Use high or low concentration, again depending on the analyte that we're interested in, and then run blank, blank, SST, and then blank again. And why is this helpful to us? How we use it is that we can actually check, because this doesn't include extraction steps and all these things, right? We spike it in, we know that this sample should have this form of peak at this intensity, right? Because there's no longer the issue about whether there's an error with extraction and things like that. So we know it should have this peak, this size, this intensity. So by examining these sort of things, we can actually gain some information about the health of our instrument, okay? So for example, we can look at peak symmetry, signal to noise ratio, peak count, back pressure, trace over the course of the SST sample. So if we have a low SST that shows a missing or diminishing peak, we can consider there is a loss of sensitivity to the instrument, okay? And if there is a peak, if there's a poor peak separation, we can consider whether there is any interfering illusion. If you look at the liquid chromatography back pressure, whether it's constant or rhythmic, it can also give us a bit of a hint whether there is an issue with the instrument as well. If it's rhythmic, it could be a valve. Whenever there's a valve change, it would cause a decrease in the back pressure. Or there is a leak, a constant leak that is causing a low LC back pressure. We can also use that to check for carryover, and we can use it with all this information and all the experience that we've gathered from this sort of SST system. Then we can use it to guide a troubleshooting decision tree that we can then develop for the laboratory, right? So we can say that if you see this, it's likely that this system is problematic. If you see that, it's likely that that system is problematic, and therefore we can call the right people in to help us troubleshoot the appropriate system. And if we run this long enough, we can actually accumulate a lot of trend in our data. Okay? And it can actually, if we overlay that with our troubleshooting log, then it can actually give us a very good idea about how our instrument is aging or is performing over time. Then it would also help us understand when is any part likely to face problem, and then we can actually work on it before it becomes a clinically apparent problem. So we can refine the criteria, and we can refine the decision tree and maintenance program with that. So that's all I have. Sorry, I'm rushing through to catch up with time. And again, I'm indebted to a lot of people in Australia. This is 8 years ago, February 2010. This is the first time I met Rhonda back in Hobart. And they've been very, very kind in taking me under their wings and teaching me a lot of things. So I would like to just say a big thank you to Rhonda, as well as many of you in Australia. Thank you. If it's anything difficult, please direct it to Rhonda. Only simple questions for me, okay?
You sort of touched on the QC of multiplexed assays.
Yep.
Thanks. You talked about the QC of multiplexed assays, and you kind of touched on how confusing and difficult it might be.
Yes.
What are your thoughts?
Sure.
How do you do it right?
Sure. So again, I must qualify myself that I don't actively run a mass spec assay, but if we think about it, the ideal situation is that you would be able to customize the QC for each of the analytes, right? But it's impossible because each time when you run it, it's 14 analytes. So what you do is you cater for the worst analyte. Okay, let's say we have one analyte that has 3 or 4 sigma. It's not that good. So what we do is maybe we run more levels of QC. But how you interpret the rules will then help you mitigate the false rejection for those that are very good. Okay? So what we can do is that you run maybe 3 levels, run more levels. For the bad assay, you put in more QC rules. 1-2S, 1-3S, 4X, 10X. That means we put in the multi-rules into the interpretation. For the rest of the assays that are running very well, 1-3S. That means you would not likely to see a false rejection if we do it that way. So QC to me is reasonably simple. It's quite simple in my mind because there are only 3 things that we can change: the frequency, the concentration, and the rules that we use. So if you play around with that, then hopefully you can actually use it to optimize the detection.
Uh-oh. We don't have enough QC that actually is suitable for LCMS systems. It's all the values are based on immunoassay.
Yep.
But that's just my problem. Can you fix it for me?
Wait until one day I go to the dark side. I join the industry side. Yeah.
Okay.
Okay.
All right. Thank you.
Thank you. Thanks very much.
Thank you. And have a nice little